So what we're going to do today is we're going to keep studying these polar coordinates, or polar equations. And last time we just got acquainted with them. We saw that we could represent points on the plane or curves rather than doing it in terms of x and y, which represent horizontal and vertical distance. We can instead represent them with r and theta, where theta indicates the direction of the point and r indicates how far away the point is in that direction, or maybe the opposite direction if r ends up being negative. Now, what we're going to do today is we're going to start learning calculus with polar curves, and we're actually going to begin with doing integrals. Now, unlike parametric equations where we avoided the area under the curve interpretation, that's the one we're going to be focusing on with polar coordinates. So let's get started and take a look at that. All right, so let's imagine that we have a circle, right? Let's say it's a circle of radius r. So I'm sure we've learned forever ago what the area of the circle is. The area will be pi times the radius squared. So what I'm going to do is I'm going to make a chart. I'm going to have how much theta we go through and how much of the curve we trace out. And then I'm going to have how much area we get from the figure that's enclosed. So for example, to go around the whole circle, that will be 2 pi radians. So we go all the way around the circle, we get 2 pi. And then our area for that will be pi r squared. Now let's say that rather than going around the whole circle, we instead start at 0 and only go to pi. So we have the half circle. So let's say we do that. We end up getting top half of the circle here. We only go through pi radians for that, and its area will be 1/2 pi r squared because it's the half circle. And in the same way, we can only go up to pi over 2. That would give us a quarter circle, so we'd have 1/4 pi r squared. So you may start to notice a pattern in this table. First of all, we have an r squared on every single one of these. And it makes sense because area is measured in something squared, units of length squared. Looks like we have, now when we have an angle over here, it always seems like we have half of that on this side. So we have 2 pi here and only pi there. We have pi here and 1/2 pi there, and so on. So it seems like whatever our angle is, we always have 1/2 of that angle times r squared. And that seems to give us our area. So for example, if I want to find the area of any, what's called a sector of a circle, any kind of slice of the pie here, the area of that is going to be 1/2 theta times r squared, whatever this angle is. All right, well, that's all well and good, but we already know how to find the areas of circles or half circles or what have you. What are we going to do about different curves? Well, let's say we kind of have a more general polar curve. Maybe it looks sort of like this, for example. And let's say we start at an angle A, and then we end at an angle B. That's a theta, here will equal A. Now what we're going to do is we're going to break up this curve into chunks. Now the way I'm going to draw my chunks is I'm going to draw them as sectors of the circle. I'm not going to draw rectangles. I'm instead going to draw these circle sectors. And they'll all have the same change in theta value. So they'll all go through the same amount of angle. So measuring my area going like that. Now the change in angle of each of these, since it's going to be really small, we're going to represent that as d theta. So what we're doing is kind of like with the integrals we've done before, we're having more and more of these sectors, but they're all getting more and more narrow. They're spinning through less and less angle each time. Now notice that even though we have a d theta for our change in angle, this length here, r, that's not going to be dr. It's actually the full length of the curve. So that's just going to be regular r. So the area of each one of these chunks will be 1/2 r squared d theta. So as we send our limit of a number of chunks to infinity, what we end up getting is an integral from a to b of 1/2 r squared d theta. This is where we add up all of those tiny chunks together. And of course, all these curves don't have to be circles. Like this pretty clearly isn't a circle right there. The actual sector of a circle would look more like that. And of course, it's not perfect, but as we have more and more of these sectors, the approximation is going to get better and better. So this is one way of looking at the area swept out by a curve. Another way of looking at it is 1/2 the integral a to b of f of theta squared d theta. Because oftentimes we have r as a function of theta. And when we have that, then we just put whatever our function is in here, we square it, and then we do the integral to get the area. All right, so let's see an example of this. See how this is going to work out. So let's say I have the polar curve r is 1 plus cosine of theta. And this curve was actually on the previous worksheet, and in that worksheet we were just drawing them. So let me draw this out real quickly. So this curve starts here out at 2, it kind of comes around, it crosses only through 1 right there, and then when it goes to pi, it comes into 0. And then because this is an even function, or we could also see it by plotting more points, it ends up looking exactly the same, just a mirror image on the bottom. And by the way, this curve has a special name. This is called a cardioid because it kind of looks a little bit like a sideways puffed up heart. This is called a cardioid. All right, well, let's say we wanted to find the area enclosed in this cardioid. Now, the way I'm going to draw my area is a bit different from the way we do integrals, or from rectangular integrals. Normally for those, we kind of just draw rectangles up and down. But here what we're doing is we're always drawing a bunch of lines from the origin to our curve. And we're imagining that each one of these is like a circle sector that we're finding the area of. If we break it up like this and we add all of those together, then we'll end up finding the true area within this curve. All right, well, let's see here. So let's set up our integral. We have the integral of 1/2 the integral from 0 to 2 pi. In this case, I go from 0 to 2 pi because I start drawing my curve at theta equals 0. Here I end up at pi, and then there I end up at 2 pi. So to get the whole curve and the whole area, I need to go from 0 to 2 pi. And then I have my r squared, which will be 1 plus cosine of theta, quantity squared, d theta. So this is the integral that we need to do. All right, well, let's get a little bit of review in for doing an integral like this. So the first thing we're going to do is we're going to square the inside. So I have 1 plus 2 cosine of theta plus cosine squared of theta d theta. So this is going to be my integral right here. Now we know how to integrate 1. We know how to integrate 2 cosine of theta. That would just be 2 sine of theta. But this guy we need to modify first. So remember our half angle formula. This is the same as 1/2 plus 1/2 cosine of 2 theta. So I'm going to combine this 1/2 over here. So I end up having 1/2 the integral from 0 to 2 pi of 3/2 plus 2 cosine theta plus 1/2 cosine of 2 theta. So now everything inside this integral is something that I can end up doing. Let's see, I'm going to erase this part. I want to keep my picture for a moment. So when we do the actual integral, we have 1/2, and then we have 3/2 theta plus 2 sine of theta plus 1/4 sine of 2 theta from 0 to 2 pi. So remember, the integral of cosine will be sine, and the integral of cosine of 2 theta will be sine of 2 theta, but then we have to divide by that extra 2. All right, now let's go ahead and plug in our bounds here. So I put 2 pi in for this. All right, what does that give me? Well, I have 3/2 times 2 pi, that will be 3 pi. 1/2, and then I have 3 pi. Then I plug 2 pi in for my sine. Sine of 2 pi is 0. I plug 2 pi in for sine of 2 theta. That'll be sine of 4 pi, also 0. And then finally, when I plug in my bottom bound to all of these, we'll have a 0 here. Sine of 0 is 0. Sine of 0 is 0. So it looks like despite all those terms, we only end up with this one right here. So it looks like the area enclosed in this cardioid is 3 pi over 2. That's kind of a basic example of how we do these integral problems and finding the area enclosed within polar curves. Now, before we move on to the next example, I want to highlight something that's really important. So notice that when I drew this, I kind of drew the area over the whole shape. But notice how this shape is actually symmetric. So what I can do is instead of going over the entire area, I can instead go over the top area and then just double that, because this is an exact copy of that. So if I find two of these areas, I'll actually get the area of the whole thing. So rather than doing the integral I just did, alternatively, I could do 2 times half the integral from just 0 to pi. That will get my top half right here. And it'll be the same integral. 1 plus cosine of theta squared d theta. So sometimes it's a bit easier to use symmetry to do these integrals. So we have 2 times a half, that would cancel out. So this integral is exactly the same, and then we would end up getting 3 pi over 2. All right, looks like we have a question. Isn't it incorrect to not include everything under the integral in parentheses? So you don't need to do that as long as you have your integral in front and d theta at the end of it. You don't need to have everything inside of parentheses. That's not really required. So yeah, it's okay if you don't do that. All right, so we found the area of this cardioid. Now this integral isn't much easier to do than the previous one. It's just the coefficients change. But for the next one, we're going to see that we need to use symmetry in order to do the problem at all. So for my next curve, the next one we're going to look at, this one's going to have the equation r squared is cosine of 2 theta. Now, I'm not going to, I think this is one that we didn't see before on the previous worksheet, so I'm actually going to go through how we draw this one. And drawing this one is a little bit strange, so pay close attention to this. As usual, I'm going to plot points to draw this, but instead of just having theta, I'm going to have theta, r squared, and then r. And we'll see why we make that distinction in a second. Okay, so here's our axes right there. Why don't we start by plugging in theta equals 0, like always. If I plug in 0 here, I have cosine of 0 is 1. That means r squared is 1. But if r squared is 1, then r itself is actually plus or minus 1. Negative 1 squares to 1 and 1 squares to 1. So what does this mean for the curve? Well, what it means is we actually have 2 different points that satisfy the equation with theta being 0. So we have one out here at positive 1, we're going to point there. And then we want to have one out here at negative 1. So we're actually going to put 2 points there. Now, what I'm going to do is I'm going to go to pi over 8. Usually I don't go this finely with my change in theta, but I'm going to do this to illustrate what's happening here. So I plug pi over 8 into here. I have cosine of pi over 4 because I double it. And cosine of pi over 4 is root 2 over 2. Now remember, that's equal to r squared. R squared is root 2 over 2. So when I want r, I actually have plus or minus the square root of 2 over 2, which is actually a very fancy way of saying 1 over 2 to the 1/4 power. But once again, so this is a number that's pretty close to 1. I think it's like 0.8, 0.9 something. So what we do is we go in the pi over 8 direction, kind of a smaller angle, and we end up coming in like this. Remember, we also have the negative 1. So on this other side here, we're also going to be going in like that as well. So it's almost like we're kind of drawing 2 curves at once, and they're doing exactly the same thing, just flipped over. Now, if we go to pi over 4, that'd normally be what we would plug in next. That'd be cosine of pi over 2, since we double it. Cosine of pi over 2 is 0. And then that means that r will also be 0 as well. What's happening is we're kind of coming in, and then when we hit pi over 4, that's when we come into the origin right there. Okay, this seems kind of strange. Let's keep going with this. Let's see what happens. Let's go to pi over 2. So if I put pi over 2 into here, I have cosine of pi. Cosine of pi is negative 1. But remember, it's negative 1, and it's in the r squared column. That would mean that if we looked at the square root of that, we'd get plus or minus I for our r. Now, this is the real plane. We only have real numbers on here for x and y. So what we're going to do is, unlike this, where we actually were plotting 2 things at once, here, we're not going to plot that at all because it's imaginary. And there's no real number that will square to be negative 1. We're actually going to ignore that point. We're not going to draw anything for pi over 2. And that would actually continue. That would happen for all the angles between pi over 4 and 3 pi over 4. When we got to 3 pi over 4, if I plug that in here, I have cosine of 3 pi over 2, which is 0. So we'll have the 0 case again. So it's kind of like the curve disappears for a while, and then when we get to 3 pi over 4, we have another point at the origin. And then finally, when we move out to pi, r squared will be 1 again, and then we'll have plus or minus 1. So I pretty much resume drawing the curve at 3 pi over 4, and then we end up getting this right here. So what does our curve look like? Actually, probably won't quite look like that. Look more like this. There we go. So we end up getting this sort of infinity symbol or figure 8 looking curve, and we only had to go through pi to do that. But the thing is that even though we went through 0 to pi, we actually had to skip a large chunk of this, over half of it, between pi over 4 and 3 pi over 4, because all the points in there would have cosine be negative, and we have imaginary r values. So it's very important to not only draw double the amount of curve for this one, we don't draw any curve when we have a negative. So that's kind of the strange thing that happens when we have r squared equals something. Now that I've drawn this, so I can safely erase this table now. So what I'm going to do is I'm going to try to figure out the area enclosed in this sort of figure 8 thing. Okay, so I want to know what all of this area is. Now, the thing is, I can normally integrate from the first angle I have to the last angle. So normally that'd be like 0 to pi or something. But in this case, what I'm going to do is I'm going to notice that I have this circled area here, right? That's actually going to be 1/4 of the total area in the whole shape. Because we have this chunk up here, we have its mirror image over here that makes 2, and then we have 2 copies of that over there. So what I'm going to do is I'm going to find the area of this first chunk and then just multiply it by 4. So I'm going to have 4 times the area, so it's 1/2. 0, let's see, this chunk started at 0 and ended at pi over 4, if I recall. Now, normally we square whatever function we have in here, but the thing is, r is already squared for this. So we don't need to do anything for this cosine. That's kind of the silver lining to this problem. We're just going to put cosine of 2 theta in there because our r is already squared, so don't accidentally square it again. All right, well, last I checked, 4 times 1/2 is 2, and the integral of cosine of 2 theta is going to be sine of 2 theta divided by 2, so we're going to cancel that part out. So we end up with sine of 2 theta from 0 to pi over 4, like that, and then we plug in these points. So I have sine of 2 times pi over 4 is sine of pi over 2. It's going to be 1. And then sine of 0 is 0. So the area for my entire figure 8 right here is actually just going to be 1. So it's a little bit surprising there aren't any pi's involved with this one. So the moral of the story is sometimes symmetry makes a difficult problem way easier by eliminating unnecessary complications. Like we didn't have to think about the fact that it still won't even exist between pi over 4 and 3 pi over 4. So I encourage you to use symmetry when you can. And one final suggestion, especially for a problem like this, it's really important to actually draw the curve. If you didn't draw this and you just saw this guy right here, it might be really tempting to just do 0 to 2 pi and assume that's going to be the complete go-around. Even 0 to pi wouldn't actually be right for this. So it's important to draw the picture and understand where each part of the shape happens so you know what to set your bounds at. All right, that's all I have to say for now. So let me know if you have any questions, and I'll be happy to help you out.